Dear Chairman, thank you for your introduction. Now as I begin my presentation. Hello, my name is Wang Lijiang. I'm currently pursuing a master's degree at Shenzhen University. My supervisor is Professor Guangzhong Cao. Today I'm delighted to introduce our work at a Hall sensor-based position measurement hybrid magnetic levitation system. I will introduce my work from the following aspects. The MLS presented in this paper is shown in Figure 1. The system consists of a magnetic drive unit, a levitated object with a solid cylindrical permanent magnetic, and a DSP-controlled system. The MDU has 12 hollow cylindrical permanent magnetics and 4 iron core electromagnets. The hollow permanent magnetic array of the MDU can form a permanent magnetic field. See Figure 2, which provides part of the levitation force applied on the levitated object. Therefore, the permanent magnetic array plays a key role of reducing the energy consumption of the MDU. The bottom plate, which made of printed circuit board (PCB) in Figure 2, is used to mount the sensors and electromagnets. The 4 electromagnets are used to form a desired magnetic field to regulate the position of the levitated object. The linear Hall effect sensors are installed in the center of the bottom plate to measure two-dimensional horizontal motion of the levitated object. The DSP controller acts as the central processing unit to first calculate the position of the levitated object based on position feedback from the linear Hall effect sensors, and second, to output current to drive the electromagnets. Finally, a personal computer is used to communicate with the DSP controller based on UART and monitor the levitation system. As a typical application of magnetic actuators, magnetic levitation system (MLS) has been a popular research area in nowadays. MLS can be used in special environments and realize contactless operation due to the reason that there is no mechanical contact. These environments, which require contactless operations at a micro scale, include such as operating inside the human body, micro manipulation robot in clean room, and biomanipulation. To achieve precise motion control of the MLS, the optical-based devices, such as laser sensors or camera, are generally used to measure the position of the levitated object. However, there is an obvious limitation for the operation in a non-transparent environment. Hence, this paper presents a Hall sensor-based position measurement of hybrid magnetic levitation system (MLS) developed in the laboratory for applications of contactless operations and a micro scale. The magnetic field of the MDL is produced by 4 iron-core electromagnets, 12 hollow cylindrical permanent magnets, and 1 solid cylindrical permanent magnet. On account of the magnetic field superposition principle, the analysis of the magnetic field can be simplified to a problem that to analyze the magnetic field of a solid cylindrical permanent magnet and an iron core electromagnet. Using the current model, the magnetic field produced by a solid cylindrical permanent magnet at a random point P, X, Y, Z in free space is equation 1. In order to simplify the following expression, as the laying position of the cylindrical permanent magnet is given, equation 1 can be rewritten as a function of R. Based on equation 2, the magnetic field produced by a hollow cylindrical permanent magnet used in the MDU is equation 3, where R out and R in are the outside radius and inside radius of the hollow cylindrical permanent magnet. Here, the magnetic model of the permanent magnetics in the MLS is defined. And then, the magnetic field produced by a single iron core electromagnet at point P, X, Y, Z is equation 4. Based on the above discussions, the magnetic model of the MLS is given by equation 2, 3, and 4. There are 3 magnetic field sources in the MLS. A solid cylindrical permanent is the levitated unit. The permanent magnets and the electromagnets are used in the MDU. In fact, when the Hall effect sensors were installed in the magnetic drive unit, only the position of the levitated object changed, and current supply to the electromagnets change caused the electromagnetic field measured by the linear Hall effect sensors changed. Therefore, the key to the installation of the linear Hall effect sensors is to find a position will not be affected by the electromagnet's magnetic field, so that the position of the levitated object can be obtained from the change of the magnetic field measured by the linear Hall effect sensors. To find the laying position of the linear Hall effect sensors, using equation 4 to explore the magnetic field distribution of an electromagnet. The electromagnet used in the calculation model has the following geometric parameters: n equals to 500 turns, r subscript out equals to 10.5 millimeters, r subscript in equals to 4.5 millimeters, and L equals to 22 millimeters. Figure 3 shows that no matter how the current applied to the electromagnet change, the horizontal components of the magnetic field and the height of L divided by 2 are always 0. The laying position of the linear Hall effect sensors is determined, see figure 4, based on this characteristic of the electromagnet. Hall sensor H1 and H2 are used to measure the magnetic flux density in horizontal direction. H3 is used to measure the magnetic flux density in vertical direction, by the way. According to this installation of Hall sensors, the interface of electromagnets to the sensors can be ignored. On the other hand, due to the fact that the magnetic field generated by the permanent magnet in MDU is a static magnetic field, the measured values of Hall sensors only change with the position of the levitation unit. In fact, the nonlinear relationship between the position of the levitation unit and the measured value of the Hall sensors satisfies Formula 1. However, Due to the complexity of equation 1, it is difficult to obtain the position of the levitation unit directly from the magnetic flux density information. Therefore, a solution model for the position of the levitation unit based on BP neural network is designed, and a process structure is shown in Figure 5. The training data of the neural network come from the finite element model, FEM, via ANSYS Maxwell software. The value range of FEM is X in the range of -60 mm to 60 mm, Y in the range of -60 mm to 60 mm, and C in the range of 37 mm to 47 mm. Figure 6a, Figures 2b, and Figures 2c show the magnetic field of the HMLS as C equals to 37 mm and I equals to 0A. The proposed position measurement of the HMLS is validated by FEM analysis, and the error caused by the noise in sampling circuit is ignored in the simulation. Parameters of the HMLS is listed in Table 1. Figure 6d shows the position of the sampling points for the magnetic flux density of the levitation unit. By analyzing the sampled data, Figure 6e shows the results of the proposed solution model. According to the simulation results in Figure 6d and Figure 6e, the solution position approaches to the desired position, where the maximum absolute errors of x-axis, y-axis, and z-axis are 1.3 times 10 to the power of -3 millimeters, 1.2 times 10 to the power of -3 millimeters, and 1.3 times 10 to the power of -3 millimeters, respectively. The maximum relative error are 0.0065%, 0.6665%, and 0.180%, respectively. The effectiveness of the proposed method is verified. The analytical nonlinear modeling and the installation of the linear Hall effect sensors were presented for the MLS developed in the laboratory, which is to show the potential application in the contactless operation for the magnetic levitation system. The results of the finite element analysis verified the effectiveness of the nonlinear modeling of the MLS. Experimental device is developed based on the analytical nonlinear modeling. The future work will be focused on the effective control method of the developed MLS by employing the linear Hall effect sensors to detect the position based on the analytical nonlinear model. Thank you for your attention. That's all of my presentations.